Hello, and thank you for coming to my talk, Distortion and Ghosting-Free, High-Resolution Ex Vivo Human Brain Diffusion MRI up to p-values of 50,000. I am Gabriel Ramos Llorden, and before going to this project in detail, I would like to situate this oral presentation in the broader picture of the Connectom 2 project, a project that we are developing at the Martino Center, where we are developing the next generation of human MRI scanners for bridging studies of the macro, meso, and micro connectome. On top of developing the next generation of gradient system, we are interested in doing the multi-scale validation with diffusion MRI, micro-CT, and electron microscopy. And in this validation, ex vivo diffusion MRI plays a very important role because it's ideal for mapping the mesoscale structure of the human brain with unprecedented detail. And this is because we can achieve much higher spatial resolution than in vivo diffusion MRI because we don't have time constraints, we don't have motion, and we can use a specialized pool sequence that renders high SNR, like 3D multi-shot EPI. All of the information derived with the ex vivo diffusion MRI can be translated to in vivo diffusion MRI. So this technique is key. It's a key bridging technology for understanding, for mapping the human brain. Nevertheless, there are some peculiarities with ex vivo diffusion MRI. One is the fact that because the diffusivity of the tissue is reduced, to provide enough diffusion contrast, we have to use much higher p-values than normally we used with in vivo acquisitions. So if we want to have high SNR, we have to get a short acquisition time, which the only option is to use gradient systems with ultra high gradient strength, like the Connectom system. One of the problems with these powerful scanners is that the strong gradients create eddy currents that affect the image readout, and that introduce perturbation, phase perturbation in the K-space encoding, which is not, if it is not properly accounted for, create ghosting, extremely ghosting, and distortions, which invalidates all of our analysis of diffusion MRI. Even conventional techniques like linear phase correction that is included in any Siemens scanner are insufficient here because they do simplistic assumptions of the phase variation between odd and even light EPI, which definitely do not hold when we use ultra high gradient strength. So clearly for ex vivo diffusion MRI, we need superior techniques. We need more advanced reconstruction approaches. One of those approaches is spatiotemporal field monitoring. The idea is that with a field camera, we can measure the spatiotemporal variation of the main magnetic field, and that gives you complete information of all of the perturbation phase as well as the K-space trajectory. We have a field camera in our scanner where we fit the phase, the measure of the phase, to a basis of solid spherical harmonics, where the first order represents the K-space trajectory, the third order indicates the V0 term, and the second orders and third order terms are unwanted components that we would like to be minimized. But as you can see here, we have observed that second order and third order terms are substantially higher, and this creates a strong ghosting that cannot correct with the linear phase correction. Nevertheless, because we are lucky and we can measure the spatiotemporal field variation completely, we can change all of our framework for reconstruction and develop a reconstruction techniques that are phase informed, and they can incorporate all of these variations in a model-based approach. Indeed, because we have the phase, the measure of the phase, we can fit the data to a spherical harmonics. We can create what is called the encoding matrix, which is a complex exponential where the phase is given by this equation. We have the co-sensitivities estimated from a gradient recalled echo sequence that we can acquire prior to the scan. If then we have the acquired K-space data and X is our ghosting free, we can formulate this linear least square problem with Tikhonov regularization and solve for X, where because we have been including the phase variation in the model, we can achieve ghosting free images by solving this very easily reconstruction approach. It can be shown from these results that ghosting is indeed well reduced when model-based reconstruction with high order terms is implemented, as you can see here on the right, compared to the conventional reconstruction of Siemens. And this is, we have demonstrated that this improvement is consistent over the whole brain. See here axial, sagittal, and coronal slice of a 3D multi-shot EPI dataset acquired at 0.8 millimeter for B values of 4,000. Note that the ghosting is clearly reduced compared to the linear phase correction approach. And of course, this has an impact on diffusion MRI analysis. If we don't do any correction at all, not only we have visually unpleasant images, but also we are biasing all of the connectivity measures. We are biasing the phase, as we can see in the red square that I am pointing out here. We are biasing the orientation of the primary eigenvector of the tensor. We are biasing any tractography results. As a result, we are biasing the phase. And of course, we also suffering from unwanted artifacts in the mean diffusivity, which can be well corrected with our technique because we are incorporating high order terms in the image reconstruction. Another benefit, before going to another benefit, also this of course has an effect in more advanced diffusion models like DKI. And another benefit that I would like to address, that I mentioned in the title of this talk, was the fact that we can achieve distortion-free. Of course, we know that there are very popular techniques like eddy from FSL tool that can correct for eddy current distortions by doing a registration. Nevertheless, this registration is not always perfect, especially if we go to super high B values like 50,000. And also, even in the case that the registration it's accurate, it always leads to blurring in the reconstructed image. And this is because the image registration always needs an interpolation. And no matter if it is cubic, this is going to blur the image substantially. And maybe this is not a super important issue when we are dealing with low resolution diffusion MRI, but definitely when we go to high resolution diffusion MRI, like in vivo, and we want to observe or to measure microstructure in areas like the hippocampus, this is gonna have a huge effect. As we can see here on the image on the right, with our high order image reconstruction technique, this is not a problem because it's a one-step approach, and all of the information is incorporated in the reconstruction step. As a conclusion, we have demonstrated here that ex vivo diffusion MRI requires advanced case-based reconstruction to deal with ghosting, because the strong eddy currents created with ultra-high gradient strengths create phase modulation that are not well modeled with the conventional techniques. They fall short, and model-based reconstruction approaches like the one we are presented here, where we measure the spatiotemporal variation of the main magnetic field, and we solve the reconstruction problem as a phase-informed inverse Fourier problem, leads to much better reconstructed image, ghosting-free, that leads to improved downstream analysis, and also images with less distortion and less blurred with high resolution. We also expect that this technique can be translated to in vivo diffusion MRI. And this is the end of my talk today. I hope you have enjoyed the talk, and please don't hesitate to contact me if you have any questions.